So lengths as integrals, areas as double integrals, and volumes as triple integrals. This title is meant to be provocative because when you think about integrals, you don't think about lengths, but areas. And double integrals correspond typically to volumes and triple integrals hypervolumes. So how can we use integrals to get lengths? Okay, let's take a look at what we mean by that. So the simple way to find the length of an interval is to just so if we have this interval here from a to b, is to subtract a from b, and b minus a would then give you the length of this interval. Well, what if instead we created this y-axis and let our function be equal to 1. Okay, so y is equal to f of x is equal to 1. We have the constant function. Well, then what's the area here going to be in green? It's going to be the integral, right? We integrate the function 1 over dx from a to b, and we get b minus a. Notice in both procedures we got b minus a, and so what we learn from this is that the integral of a function equal to 1 will correspond to an area that is in fact equal to the length of the interval. Okay, so the area here is the same as the length here. Now, if these quantities had units, okay, if we were dealing with physical quantities and this was an actual height, so that you actually have 1 meter, so that the function is equal to 1 meter, then dx also has units of meters, so we're multiplying meters and meters, and so we should get meter squared. This would be b minus a meters squared in that case, whereas here we're subtracting lengths, so we should get just meters. Now, the values will be the same, the units will be different. But in mathematics, when we're not dealing with physical quantities, we don't have units. So that this correspondence actually works. If you want to compute the length of an interval using an integral, just let your function be equal to 1. Then your area will actually be equal to the length of the interval. We could do something similar with double integrals. So the traditional way of getting the area of some region in the xy plane is, say it's bounded by some function up here, h of x, and some other function below, g of x. Then what one learns typically in a calculus 2 class is that to find the area of that region there, one should integrate a to b of this integrand, h of x minus g of x. Okay, so the integral of just h of x would give you the area of everything under the curve, okay, of h of x, and the area on the integral over g of x should give you the area below g of x. And so when you subtract the total area here from the bottom area, you'll get the area of the region. Now that's sort of the traditional way, and it makes sense in terms of units that you get an area. These would have units of, say, meters there, and meter minus meter, you just still get meter, and this is also meter, so you'll get a meter squared. Okay, so makes sense. Well, another way to compute the area is to use a double integral, but to set your function equal to 1. So this is now a function of 2 variables, and we're going to let it equal 1. So you just have this, it would be a plane equal to 1. And notice then that when we do the double integral over the region R of the function 1, we actually compute the volume of this shape that you see here. But since the height is equal to 1, the volume is actually the same as the area of the region. Okay, so there's a similar correspondence that we had above. Here, the volume equals the area, and so although this dA would have a unit of meter squared, and this one would have unit of meter, so that this expression, if we had units, would give you a meter cubed, which is a volume. If we don't use units, we're not dealing with physical quantities, then the volume and the area will be equal when we use the function equal to 1. Here we see another visualization of this concept. Okay, so notice here that the height is equal to 1. Our function is just equal to, our function of two variables is just equal to 1. And because a volume is the area times the height, well, if the height is 1, then the volume coincidentally is also equal to the area. And so we could use double integrals to compute areas of regions if we let our integrand equal 1. Taking this concept one dimension further, okay, we could use triple integrals to compute volumes. Okay, now typical way to compute a volume is to carry out a double integral between the top surface hxy. If we just do the double integral of hxy, it would give us the volume under this surface hxy. Subtract out the volume under the surface gxy, and you get the volume between the surfaces h and g. That's the traditional way, if you will, to compute a volume. And notice these are heights, so you'll get a unit of meter here and a unit of meter squared for the dA, and you do end up getting a meter cubed for the volume, as we would expect. Now, what we could also do is the same trick of using a function equal to 1. Okay, now this is a function of 3 variables. We can't plot this in 3D space, right? We would need a fourth axis, a W axis, which is not simple to visualize. Although if you wanted to, you can quote plot this function 1 by just coloring a consistent color of blue all around, which would then and we would then agree that this color blue corresponds to the value of the function of 3 variables equal to 1. Okay, so we would say that the if we go to a point in our space, in our domain, and we see that the color there is blue, then that corresponds to a value of 1 for our function of 3 variables. Well, doing this same trick, then we could compute the volume using the triple integral there. And notice that, again, if this had units, we would have a meters there for the hyper height, if you will. And we would have meter cubed for the volume element. And so we would get meters to the 4th if we had units, but we don't. And so coincidentally, when we use the function equal to 1, our volumes, our hypervolume is equal to the volume. So we could use triple integrals for volumes.